So the definite integral will take what we just did in 13.1 and 13.2, where we've learned how to integrate, and it's going to explain how we can find that area under the curve between, say, two x values. So these are going to be the properties that we need. This is really all you need out of the information on this first page. And that's going to be our guidelines or our rules when we get ready to integrate. Now, this first one is very atypical. You don't see this written very often. This is just explaining if I wanted to take the definite integral from some value A to the same value. In other words, let's say I wanted to start at 2 and I want to end at 2. Well, think about that for a minute. Have I moved it all on the x-axis? So guess what the area under the curve for that is? It's got to be 0. There's no rectangle there because there's no width if I'm at the same start and stop point. Now, this is explaining that if I have my limits of integration, we're going to call this our lower limit, and this is our upper limit. Typically, you will see that this is going to be the smaller number and this is the larger number. But every now and then, they may throw you this little goofy curveball, and they put the larger number on bottom and the smaller number on top. In other words, instead of going from left to right, it's like you're going from right to left. There's a little adjustment you can make that will let you find that area under the curve easily, and it's simply this. If you want to put a negative sign in front, then you can switch so you have the lower limit as the smaller number and the upper limit as the larger. Okay, that's just telling you these are going to be equivalent. Now, FYI, if they give you one of those and you don't notice, it actually takes care of itself sign-wise if you leave it like it is. It's okay. But this is the way. This is the property, because it's the proper way to do this would be to go from your lower limit to your upper. You'd want your lower limit to be smaller. So this is what the adjustment looks like if you switch those numbers on the integral. Now, this one we've already been using, because if there's some sort of constant in front of the function, what did we say we could do with it? We could kick it outside the integral sign. In other words, we can do the integration for the function, and then we just multiply times the constant when we finish, okay? This is the same thing we've been using too. If we saw we had more than one function, or if, say, in a polynomial where you've got multiple terms, then this is just explaining to us we can still integrate term by term, and then we can do the evaluation, okay? And this one, we probably won't see a need for this. This is something we do in calculus too. If, let's say, we were trying to evaluate from A to B, but somewhere in between A and B, let's say it's one of those goofy graphs where there's an asymptote. So we've actually got a break in the graph somewhere in between A and B. This would tell us that we could pick a point C, like wherever that break is, and we could get what the integral is from A up to C, wherever that asymptote is, and then add from C to B. And that would give us, technically, if you've got a gap in the middle, you couldn't just go from A to B. But I could pick some arbitrary point in between, and I could get this area under the curve plus this area under the curve, and that would be the total area, okay? That, I personally think that's going a little further in depth than what you guys are going to need, but those will be our properties. Now, the first part of this, we're not actually going to do. We're just going to do this page in 13.4, and then we'll look at some more examples in 13.5. So this is asking us to evaluate, instead of the indefinite integral, it's the, what kind of integral? Definite integral, because I now have a lower limit and an upper limit on my integral sign. So the only thing I'm going to do that's extra is after I integrate this, I will no longer need a plus C. I'm going to actually put in these limits of integration, and I'm going to get an actual number that will represent the area under the curve between this equation, this function, and the x-axis if I move from 0 to 7 on the x-axis. That's exactly what it means. If I were showing it to you visually, I'm going to put this in my calculator. And if I were to type in (2x squared), and I wanted to graph this thing from x equals 0 to x equals 7. Okay, I actually need a larger Y scale. Yeah, it went off the screen. Let's go to, let's see what happens if we do 100. Okay, that would be my graph. And what I'm looking for is going to be the value of this area under the curve, between the curve and the x-axis. That's what I'm interested in. Okay, so can we integrate 2x squared? That integration is pretty easy, correct? What's it going to be? All right, because I would have, you think it's going to be 4x, or are you differentiating? That's differentiating, isn't it? If I'm integrating, it's going to be what? 2, and then the x squared becomes x cubed over 3. That's the integration for 2x squared, right? Now, here's the new part. After we get it integrated, we're going to drop the integral sign, just like we did whenever we were doing indefinite integrals, but we're going to put a bracket around this, okay? And it's okay if you want to put it on the front, but you have to have it at the end. And at the end, we'll put from 0 to 7. So here's what we're signifying. We've now integrated this function. That's what we've got here. Now we are ready to evaluate it from a lower boundary of 0 to an upper boundary of 7. Okay, so here's what I would do. You want to set 2 sets of brackets, and what we're going to do is take our upper value minus our lower value. This is actually called the fundamental theorem of calculus, which is what we're going to be talking about in 13.5. And that's why typically you would have the lower on the bottom and the upper on the top, because you would expect I'm going to have more here and I'm going to take away this part. So we're going to put 7 in for x. We'll have 2 times 7 to the 3rd power divided by 3. And we're going to subtract 2 times 0 to the 3rd power divided by 3. Now all I got to do is clean up. If I take 7 to the 3rd power, what does that equal? You guys getting 343? Yeah. And what's 0 times anything? 0. So if I multiply 2 times 343, I'm going to get 686 divided by 3. That's my exact area under the curve, okay? Now, I could turn it into a decimal, but if I did, because it's divided by 3, it would be a repeating decimal, all right? 3 does not go into 686 evenly, so I would leave it in fraction form so it stays exact, and you're not giving me a rounded decimal value. Let's look at another one. Okay, what do you notice about number 6? This is one of those kind of goofy ones where they put the smaller number on top, the larger number on bottom. So how did they tell us we could fix it? Put a negative in front, then we can put the 0 on bottom, the 4 on top, and now we're ready to integrate 7x. Now that's not too hard to integrate, is it? What is that going to give us? Do you all agree with Hannah? 7x squared over 2. And I need my bracket there, and I will put 0 on bottom, 4 on top, and we're ready to evaluate. How many sets of open brackets do I need? 2. That's right. 1 for the upper minus 1 for the lower. So in this upper, I'm going to have 7 times 4 squared over 2 minus 7 times 0 squared over 2. You may be wondering, do I have to write that part out? I'm going to encourage you, yes, I would, because if I'm grading this and let's say you don't show me this part and you do something silly computation-wise, like maybe you forget to square the 4 and you do 7 times 4 is 28 divided by 2 and it's 14. If you've at least written this, you get more partial credit than if you go from here to a mistake. You know what I'm saying? So I would say, show me how you plug in, then you're going to clean up. And that's going to be 7 times 16 over 2 minus, this is just what? 0. Now, what's this going to turn into? 56. Exactly. Now, by the way, I have done something silly here. What did I leave off? I sure did. Let me go back and fix that. There should have been a negative in front of here, and there should have been a negative in front of here, which means there should be a negative in front of here. So it's not actually going to be 56. It's going to be what? Negative 56. Now, you may be wondering, why would this be a negative 56? And oftentimes when you get negative, that would be because you might be looking at the area below the x-axis. So sometimes that's why a negative shows up. Okay? Now,
negative because the bottom number was bigger?
And it's negative because in this case the bottom number was bigger. Mm-hmm.
You said if we leave it the other way, it's going to end up the same.
Yeah, if you had done it the other way, let me just show you real quickly because I have it written out here. If we had left the 0 there and we didn't bother with putting the negative in front and switching them, it would have turned into 0 minus, and then we would have had the 56. Well, 0 minus 56 is a negative 56. So I'd have the same answer. So I'm going to tell you that now a purist in calculus would fuzz up at that, but I'm going to tell you still get the right answer if you don't switch it and put the negative in front, okay? Does anybody see a shortcut on 7?
It's good. Yeah.
The limits are the same. I don't have to do anything other than say that's going to be 0.
And we need that pile of those on the test.
Yeah, those would be good, wouldn't they? Yeah. Nice and easy.
I was like, that's 0. I was like, there's no way that she's 0.
That's it. I know. You probably will not see many of those, but if you did, that's how you would answer it. So go ahead.
At least
That's the request. Put at least 5 on the test. Yeah, well, don't count on it. Okay. Fundamental theorem of calculus is what we just used, and that is simply saying this. If I have a function and it's continuous on some interval, so remember how I said earlier, if you had a break, like an asymptote, that's an issue. So this is saying we're not going to have any kind of break here. This is going to be a continuous function between these two values on this interval. Then when we find the antiderivative or the original function, then this integral going from the lower boundary to the upper boundary will be, when we get this thing integrated, it turns into capital F instead of lowercase f of x, and we will evaluate it with the upper number first minus evaluate it with the lower number. That's just what we did with the brackets, okay? And we're not actually going to do the average value But if you ever need it, it's here, okay? So let's just see if we can evaluate some more of these integrals. That means now we may see some new substitutions as well. Some of our integration may get just a little bit more challenging than the last three we looked at. So let's see if you guys can tell me what you would do with this. Is it ready to integrate like it is?
Yes.
It is. I have no reason for a U substitution because I can just integrate term by term, right? Okay. So tell me, what do you get when you integrate 8x to the third? 8x to the fourth over 4. I can clean that up in a minute. Plus, how do you integrate 3? Oh, you're differentiating. Be careful. 3x. Yes. Remember, it's like an x to the 0 power. So when I add 1 to the exponent, it turns into 3x to the first. And this has to be evaluated from what goes on the bottom? 1 on the bottom and 5 on the top. Now, if I were to clean this part up, the 8 on top, 4 on bottom means this turns into what? Yeah, 2x to the fourth plus 3x. If you want to rewrite that before you evaluate, you can certainly do that. Okay. So what would you write on your paper now?
2 sets of brackets.
Good. 2 sets of open brackets. And what kind of sign between them?
Minus.
Yes, very good. You got to subtract. So the first one has 2 times what goes in for x?
5.
Yes, 2 times 5 to the fourth plus 3 times 5. And then we're going to subtract 2 times 1 to the fourth plus 3 times 1. Okay, might want your calculator here. 5 to the fourth, I'm pretty sure is 625. And 625 times 2 is, so I've got 1250 plus 15 for my first bracket, minus, what am I going to get in the second bracket?
5.
2 plus 3, which is 5, right? So 1250 plus 15, that's 1265. And 1265 minus 5 is? That's my answer. Okay.
Exactly what we just did.
That's what?
That's pretty much what we just did.
Yeah, that's pretty much what we just did on the other. Okay, now let's look at number 2. Can we integrate 2e to the x?
Yeah, it's 2 either way.
See, that part looks good, doesn't it? 2e to the x, but I need to evaluate it from 0 on bottom, 3 on top, right? Okay. What is going to be in my first bracket?
2e
2e to the third power, and then I need a minus sign, and the second bracket becomes, okay, now can I clean this thing up? What do you notice might be able to be simplified? Say it again.
2e to the 0.
2e to the 0. What is anything raised to the 0 power?
1.
And so 2 times 1 is 2. That second bracket cleans up to just be the number 2. Now, if I'm leaving an exact answer, am I done? I am. Because remember, e is an irrational number, so I could get a decimal approximation. But if I need an exact answer, it's going to be 2e to the third minus 2. And that would be it. Okay? If they'd asked us for a decimal approximation, we could use the E button in the calculator and come up with that.
Cool.
Yes, ma'am?
So on the test, you want that and not
Well, this is the actual answer. It's the exact value. If I want you to give me a decimal approximation, it will say approximate the number to the nearest thousandth or 4 places to the right of the decimal, something like that. So if it doesn't tell you how to approximate it, then you leave it exact if E's involved. Okay, I heard an ooh. Did somebody get excited about number 3? It's 0. That's the one you were looking for, right? Okay. It's 0, and it's because our limits of integration are the same for our upper and lower boundaries. Okay, number 4. What should we do here? Okay, I'm hearing 2 different things. I heard one recommendation for a U substitution. I heard another recommendation about bringing something to the top. Look carefully. Do we need a U substitution?
No, because there's no.
We actually don't, because if this were U, du would just be dx, right? Okay, and I don't have any extra variables floating around. It's only if I've got variables in more than one factor that I have to worry about a U substitution. So I don't think I need a U substitution, but what do I probably want to change? The radical needs to become what? It's going to be raised to the 1/2 power. Now, if I leave it as a fraction, that's x plus 3 to the 1/2 power. But then I heard somebody say something about moving it to the top. Is that a good idea? Yeah, it is. So if I rewrite this so it won't be a fraction anymore, it's going to be 5 times what? Good. X plus 3 raised to the negative 1/2 power. Okay, is this now ready to integrate? Yes, it is. I've got the larger number on top, smaller on bottom. This is good to go. So what do I do with this 5? Oh, be careful. I can kick it out, can't I? It's just a factor. It's a scalar. So this 5 I could put in front of the radical if that helps me, because now the only thing I'm really integrating is the x plus 3 raised to the negative 1/2 power. You don't have to kick it out. When I would kick it out is if you are working with a fractional exponent, and the fact that it's there may kind of bother you. So if you go ahead and kick it out, now if we integrate, what is our pattern for integration? We do what with the exponent? Add 1. And if I'm adding 1 to this fraction, it's the same thing as adding 2 over 2, right? So I'm going to have 5, and then as I'm integrating, I know I have this x plus 3 raised to the, what's my new exponent? Positive 1/2, but then I have to do what else? Divide it by positive 1/2. But I probably don't want to leave it written that way, because instead of dividing it by positive 1/2, I want to turn it into what? Times 2 over 1. So I could think of this as 5 times 2 times this. So that's 10 times the x plus 3 raised to the 1/2 power. And we're going to plug in, going from a lower limit of 13 to an upper limit of 22. We okay so far? All right. So let's see if you guys can tell me what we're going to have. I need the 10, and that 10 gets multiplied by everything I do when I use the fundamental theorem of calculus here, right? So I'm going to put a bigger bracket with the upper minus the lower inside. So I don't forget everything when I finish gets multiplied by 10. Does that make sense? Okay, so plug in 22, and what will we get? 22 plus 3 is 25, and that's raised to the 1/2 power. Now let's plug in 13. 13 plus 3 is 16, and 16 is getting raised to the 1/2 power. I think I can clean those up, because something raised to the 1/2 power is the same thing as doing what? Not dividing by 2, but taking the square root. There you go. If you wanted to, think of it as the square root instead of leaving it with the fractional exponent. And that makes it easier to see. The square root of 25 is 5. Square root of 16 is 4. So in this bracket, I have 5 minus 4. How much is that? 40. And 10 times 1 is 2. Ta-da. How we doing? Okay. So we have just a couple more examples, and we'll call it a wrap. All right, look at number 5. Put on your thinking cap for a minute. What do you notice?
We need to use it because there's more than one.
We need a U substitution. You're exactly right. And I know that because I've got 2 factors here and they both have variables in them. So what would we want U to be?
3x to the 4th plus 2.
Good. 3x to the 4th plus 2. Now tell me, what does that mean DU needs to be? 12x dx. 12x to the 3rd dx. Now let's double check and see if we've got everything we're going to need. So I already know this is going to be my u to the 6th, right? I have 2x to the 3rd dx, but I need a 12x to the 3rd dx. Can I make that work?
Yes.
If I do what? I need to multiply this by 6, so I'll have everything I need for the du. But if I'm going to multiply it times 6, I also have to do what? There you go. I need to multiply by 1/6 because the 6 times 1/6 balances out, will cancel out, become 1. And now I'll have everything I need for the du. And I should be ready to integrate. So tell me what you would write down.
1/6.
1/6.
And then also
That's right. The definite integral from,
u to the 6th.
well, let's go ahead and put our limits on here. 0 to 1. And you're right. It's going to be u to the 6th du. That integration's not scary, right? This looks scary. This doesn't. So integrate for me. Do I keep the 1/6? And how do you integrate u to the 6th? Over 7, right? Now, I can kind of clean this up a little bit because that could be written as what? U to the 7th over what number on bottom? 6 times 7 is 42. Okay, now we are at the point where what did we have to do before we stopped when we were doing this in 13.2? If we did a U substitution after it was integrated, we had to be sure we go back and do what? Replace the U with what it originally was defined to be, which in this case is 3x to the 4th plus 2. Do I have to do that before I can evaluate? Yes, I do. So I'm going to replace U with 3x to the 4th plus 2. That's raised to the 7th power divided by 42. And now I can evaluate that from 0 to 1. So upper bracket minus our lower bracket. And that would be 3 times 1 to the 4th plus 2. All that's getting raised to the 7th power divided by 42 minus, we've got 3 times 0 to the 4th plus 2 raised to the 7th power divided by 42. Did we just plug in correctly there? Yes, we did. Okay. All right, let's see if we can clean this up. So talk to me about order of operations. What will I need to do here? Yeah, and what's actually getting raised to the 4th power? Just 1. 1 to the 4th is 1. 1 times 3 is 3. 3 plus 2 is how much? 5. So this is 5 to the 7th power over 42, right? That's in my upper bracket, minus, what am I going to get in my lower bracket? 3 times 0 to the 4th, that's 0, plus, and 2 to the 7th will be my numerator here, over 42. All right, I think this one we're going to give a decimal approximation. Okay? So let's practice how we would do that. If I put in 5 to the 7th, divided by 42, and then I subtract, and in parentheses, I'll put 2 to the 7th, divided by 42. I'm getting about 1857.07 if I went to the nearest hundredth. Is that making sense? I mean, we could do it where we put it in fraction form, but it's not going to be done easily. It's a messy number, let's put it that way. So I would just go ahead and give it in this form.
So,
Go ahead.
did you want it to be
If on one like this, if you have one, it's gonna tell you to round to the nearest whatever. So if it gets to be, if it was like the other one where it was 363/2 or something like that, that's fine to leave in fraction form. On this one, I would not ask you to do that because with these exponents, it gets a little too big and messy. Now, technically, we are right at the end of class. I do have a couple of more examples. Hold on a second. All right, so what do you notice on 6? What shall we do? Looks like a U substitution to me. And what would you want U to be? Good, because that has the larger exponent. So x cubed minus x squared plus 5x minus 3. That would mean my du is 3x squared minus 2x plus 5, and then my dx. Now, double check for me. Did we get lucky?
Yes.
Yes, because all of this is my du, and all of the denominator was the u. So I don't think this is going to be too difficult once we figured out that we could do this u substitution. So we are actually integrating the definite integral from 1 to 2. If you want to leave the du in the numerator, you can, or you could think of it as 1 over u du. And do you recognize that integration pattern? It's a natural log. Very good. So that means this would integrate as the natural log of, what do I do with u? Put it in, I need to put it in absolute value bars because I got to be sure that it's positive. And then it's got to be evaluated from 1 to 2. Okay, what happens in the next step? Good, I've got to replace u. So this becomes the natural log of the absolute value of, and I'll put x cubed minus x squared plus 5x minus 3. And we'll go from 1 to 2. Okay. How many brackets? 2. I need an upper minus a lower because of the fundamental theorem of calculus. And now we'll put in these values for x. So the first one, x is 2. Second one, x is 1. All right. And you know what? I left off my natural log. I got to fix that. So this is going to be the natural log of all of that, and this is going to be the natural log of all of that. Very important that I have the natural log on there, otherwise this won't be right. So I'm going to get the natural log of, now what number do I get here? 2 cubed is 8 minus 2 squared is 4 plus 5 times 2 is 10. And then I have a minus 3. If you add all those together, what do you get? 11. Now, since it's a positive number, do I have to keep the absolute value bars? No. If it had not been a positive number, then I would keep the absolute value bars.
Did you put the negative inside the absolute value part?
You could, yes, you could do it as the absolute value of negative 11. minus, now over here, I've got 1 cubed, which is 1, minus 1 squared, so that's minus 1, plus 5 minus 3. So I've got minus the natural log of what number? 2. And again, since that's positive, I don't have to have the absolute value bars. Now, that answer is correct, but does anybody know how you could write it as a single logarithm? Do you know any of those log rules? This is one of the things we just covered in college algebra. You can rewrite this because a logarithm is simply a tool for finding an exponent. When do you subtract exponents? When you have what kind of problem? A fraction. This is the same thing as the natural log of 11 divided by 2. Now, I will take this. I just wanted to remind you that it is equivalent to this, okay? That would be condensing that logarithm to be a single logarithm. And I've got one more example I'm going to do, and we'll call it a course. So this is our problem. What do you think should happen with it? Looks like a U substitution. I'm so glad nobody said change your lower limit to 2. Because then that would have turned it to 0. But okay, we're going to do a U substitution. So U is what? 6x squared plus 1. What does that mean du needs to be? 12x dx. Now, if I check what I have, do you notice anything else we probably need to adjust? Okay, I am going to be missing part of what I need for my du, but look carefully. What else is there that's an issue? I got a radical, and it's got to be rewritten as a fractional exponent, right? So I'm going to do that. And instead of putting it under the radical, the 6x squared plus 1 could be written to what power? To the positive 1/2 power. Very good. That's the same thing as the square root. And here's what I'm noticing. Here's my u to the 1/2. That part's good. But I only have 3x dx and I need 12x dx. So how do I fix it? Exactly. I'd have to multiply by 4 to get everything I need for the du. But if I'm going to multiply by 4, I also have to multiply by 1/4. So that I'm not changing the value of this original function. And now I've got 1/4 times the definite integral from 1 to 2 of, what am I actually going to be integrating? Using u to the 1/2 du. Very good. Okay. What does this give you? 1/4, and then u to the 1/2 when I integrate it becomes, yeah, because if I add 2/2, I'm going to get u to the 3/2. If that's divided by 3/2, we said dividing by a fraction is the same thing as what? Multiplying by the reciprocal. So I can reciprocate this, multiply it times 2/3. And I've got a little bit of cleanup I can do. What can I do with the 2 and the 4? Is that going to reduce? 2 goes into 4 2 times. And so here's what I have. 1/, what number?
3.
Got to multiply these together. 2 times 3 is 6. U to the 3/2. And then that's going to be evaluated from 1 to 2. Does that make sense? Okay. Now what? Yes, plug in the value of u, which is 6x squared plus 1 raised to the 3/2 power, and now we can plug in going from 1 to 2. And I will tell you on this one, it's just a little bit on the messy side with the radicals that are involved. I'll show you what would be acceptable to write for an answer. So I need to keep the 1/6 times, now if I put in 3/2, look at this, I got to square 3/2. Oh, I'm sorry, I got to put in the 2 and square it. So 6 times 2 squared is 24, and 24 plus 1 is 25, and that 25 is what's getting raised to the 3/2 power. Okay, that's my upper minus, and I just decided I'd go ahead and put the 1/6 inside the brackets instead of sticking it out front, and that's fine. And then if I put in 1 squared is 1, 1 times 6 is 6, and 6 plus 1 is 7. This is the part that gets a little bit messy, because 7 to the 3/2 power is just going to be irrational. Now, if I look at 25 to the 3/2 power, and I were to change that back into radical form, what's my index on this? The 2. Remember, the denominator is your index, so it's the square root of 25, and then I'll take that and raise it to the 3rd power. Well, the square root of 25 is what number? 5. So I'd get 5 raised to the 3rd power, which is 125, and that would mean that I would have 125 over 6 for this first bracket, okay? Minus, this one is just going to stay messy looking. So if we were to put the 7 under the radical, and we know it's a square root, it gets raised to the 3rd power, and we would have the square root of 7 cubed over 6. And technically this could clean up a bit more, but I would let you write your answer as 125 minus the square root of 7 cubed over 6, because it already has a common denominator. And if you can get that, you would be good, but I don't even think you're going to see anything that messy on the test. Okay?